everyone, my name is David Broman and I will now show you how to do register allocation. And this is actually a series of videos of two videos, and the first one is on liveness analysis and how to construct the interference graph. And this is then used in the second video where I will talk about how to actually do the register allocation using graph coloring, and that is using this interference graph. So the first part is liveness analysis. And the point is there that we should figure out which variables are actually live at the same time, that are in use in the same time. By doing that, if they are not alive at the same time, we can allocate and use the same physical register. So the point is that we have a number of virtual registers that were created during the compilation, and then that we want to allocate the physical registers. And if we cannot allocate into the physical registers, we need to spill, that is, store it into the memory. So the problem is to make it as efficient as possible, to keep as much as possible in the physical registers. To be able to do that, to do the actual allocation, we need to have an interference graph. And that is an undirected graph, and where each of the vertices or nodes in the graph represents one virtual register. We will also use the term a variable here in this case. And then you have edges between these nodes. An edge between two nodes means that they are interfering. So then they cannot use the same physical register. The last part that will become in the next video is about the register allocation. That then transforms down to a graph coloring problem. The idea with graph coloring is that you allocate in such a way so that there is no neighbors with the same color. And this is a known problem, and it's also known to be NP complete. So we have no hope really to have an optimal solution, but instead we have heuristics to do this. And this is actually fairly efficient. And this approach, I mean, there are very many variants of it, but the approach that I'm showing here today is actually what's used in most compilers. So most compilers are using register allocation using graph coloring, especially in compilers that are doing ahead of time compilation. Whereas there are other algorithms, linear scan algorithms, that are faster to actually produce the results, but gives a little bit worse result. So they are typically needed in just-in-time compilation, so JIT compilers, where really the allocation time matters. So let's continue now to introduce a few standard concepts, like control flow graph. And this is the example that we will use throughout the whole presentation. It's a kind of just a running example. It's called foo, but it has no real meaning. It has a parameter, it's got a few allocations here, and then it's a while loop. And if we construct a control flow graph from this example, it can look something like this. We split it up into basic blocks. So here we have 4 basic blocks: V1, V2, V3, and V4. And as you can see, in each basic block there is no control flow. So all control flow is between basic blocks. And this is a standard in many compilers. If we formalize it, this is just a graph. So we have a set of vertices and a set of edges. So you see that edges are defined by using just a tuple notation here. If we look at this particular graph, we have V then, so we have 4 vertices, these 4. And edges, we can see that V1 and V2 here is represented as a tuple. That is this edge between V1 and V2, V2 to V3, is between there, and so forth. And you can see also that V3 to V2, this one, is a back edge. So this forms a graph, so it's not a tree, but rather we can have circular dependencies like this one. So we've also defined some help functions. We defined the predecessor and the successor. So the predecessor is just a function from a vertex to a set of vertices, and we're using this power set notation here. And if you look at the definition of the predecessors, is using set builder notation here. So we are constructing a set here from V, and that is based on these edges. So you see here that you have V here, and then it forms a set from all the predecessors of this set using the edge. In the same way we can construct the successors. So this is kind of standard notation. So here we have the successor, the set of all nodes that are successor from a certain vertex. Let's look at just some examples. So the predecessor of V1 is the empty set. So this notation here is kind of often used to show where you have the starting node. So the successor of V1 is V2. So you see here V1 to V2, and it's the set, so it's a singleton set. Just so that you follow me now, let's try to define now the predecessor and successor for V2. Write it down like I did it here, and then pause the video and then check if you got the right solution. Right, welcome back. The predecessor for V2 would be the ones pointing into V2, so like V1 and V3. You see here V3 is pointing into 2. And then the successor of V2 is the ones pointing out. So you have from V2 we point to V4, and from V2 we point to V3. So these are the predecessors and successors, and we will use that during the video. Let's look at some other definitions, something that we call def and use. Def means that we are having definitions, so all the set of all variables being defined within the block. So you can see here we are defining Z, C, X, and Y. And use is kind of similar. It's basically the set of variables that are used. So here you see that we are using X and N. And this is when before potential redefinitions. So we will look at an example what this means now. For V1, def of V1 is C, X, and Y. C, X, and Y. The definition of V1 of use of V1 is the empty set. We are not using any variables there. Whereas in V2 we have the empty set for the definition, but we are using two variables here, X and N. Now in V3 it's a little bit different here. We have here that we are definitions. We have C, X. So X plus plus means actually X equals to X plus 1, and Y. But if we look at use here, we only have X and Y. So X and Y, but not C. Why is that? Well, it's because of this potential redefinition. Since we are defining C here and then using it here, it's kind of hidden. So it's actually not used. So this Z is not using any Z outside of this block. It's always using this one. So that's why it does not get into the use set here. And finally, we have that there are no definitions here, but we are using Y. So this is the kind of a setup that you have to do for all vertices, and you can pre-compute this the first thing after you split it up into different basic blocks. Alright, so what we want to compute here is live in and live out. And we want to basically compute the liveness of an edge, what is happening in between. If a variable is live, it basically means that it may be used sometimes in the future. And the algorithm should figure this out. So a liveness analysis where we compute the live in variables and the live out variables from each node. For example, live in then is also a set. So for a certain vertex, we have the set of variables are live in, and live out we have a set of variables that are live out. So the question is, how do we compute these live in and live out sets? That's the main task, and we're using a technique here. It's called data flow analysis, which is kind of a very general approach that you can use for a lot of static analysis tasks. So now we'll use it for the liveness analysis. So if we look at it again here, we need to define then these equations. And here is the first equation stating that the set of live in variables, that set is equal to the set of used variable for V in both cases here, in the union with in the live out where the set minus of what is defined. So we basically in this way give an equation describing the relationship between the in and what's used and coming out. For live out, we define that as the union of all live ins of the successors of V. So you see here we have V and the successor of V, all the W, all of them connect with the union for the live in. You can see here we have a mutually recursive function here. And this is not a normal function. I mean, it's not solving any real values. It's actually solving where the values or the unknowns are sets. And the approach to solve this that we'll use is called a fixed point iteration. So we have an algorithm that is iterating until it reaches a fixed point. So here is the algorithm for the liveness analysis. So we are doing for each vertex here, we're first clearing out and setting it to the empty set. So this is kind of initialization. And then we have this while loop that is going on forever. It seems we are breaking out from it. For each vertex v, we do the following thing. So the first thing we do here is to save all the sets of live in and live out. And we just save them in something called a live out prime and in prime. After that, we compute the live out and then we compute the live in. If you look at this computation is basically just a flow equation. So we are kind of assigning now, we're taking all the set of live ins, computing the union, and then creating the live out. In the same way, we create the live in by looking at the use and the live out. We do that for all variables, and then we check, did we make any changes here? Did we change the live in and live in prime? Are they equal? If they're not equal, we're not done. So then we iterate again, and then we iterate until they are equal. And this is the fixed point. So we've reached the fixed point when we have iterated so that they are equal. So let's look at an example here. So we have these definitions here that we went through. First we initialize. We just set all of them to the empty set. Showing here, we say the live in is kind of the top of each of the basic block, and the live out is at the bottom. So this is live in for V2, this is live out for V2, this is live in for V3, and this is live out for V3, etc. The first thing that happens here is copy over to out prime. So I'm just showing it here for all of them. And then the question is, I mean, you say that for each V here, we can do it in any order. Actually, it doesn't matter for the correctness, but it matters for performance. So it turns out that it's more efficient to do it backwards, so in the opposite order of the actual control flow. So we start from the bottom and then work our way up. So let's compute the live in and out, starting with this node. So first, we came here, so we computed the live out, and that is the union of all live in. Well, the live in of the successors, but there are no successors, so it becomes the empty set. The live in is computed by getting all the uses. So the uses here, that is the set of y here, union with the live out, and the live out is right now the empty set, and then set minus with the definitions, and it doesn't matter, there are no definitions, so it doesn't matter. So it's just this use here. So we get, in that sense, the live in here as the set of y. Okay, so let's see what's next. Well, then we're computing live out from this one. That will be the union of all successors live in, and we have this one. No, we don't have that. It's a bit tricky here. It should be the empty set. Why? Because the successors of this one is not this one. The successor of this one is V2. And if you look at the live in here, it's the empty set. So that's why you get an empty set. And then we have the live in here is the use. The use here is x and y. And the out is empty set. So we get x and y. Then we have the live out here. Again, for computing from V2. V2's successor is this one. So we have a y here. And we have a successor, it's also this one, so we have x and y. So it must be, live out must be x and y. So it's a union of these two. The live in is the use, so we have two uses here, x and n, you see here, use x and n. Minus what is on the live out of v, union with the live out. So we're x and n, and x and y, minus the definition, so we don't have any definition. So that means that we have x, y, and n here, live in. Okay, we are almost done. So now let's look at the live out again for this v1, and we get this x, y, and n. Why did we get that? Well, it's the union of the successors in, and we have this one, x, y, and n. Finally, we should compute the live in, and the live in is the use, so there is no uses at all here. You see the empty set. But we have union with the live out, and that is x, y, and n minus the definitions. So what do we define here? We are defining z, x, and y. So minus set minus means that we just have left n. So the live in is n. Alright, so now we have a set here for live in and live out. Are we done now? If we look at this, we should see that the live in and live in primes should be equal, but we can clearly say these are not equal, these are not equal, and all of them must be equal. So we are not done. And we have to iterate again. So we do that, and then we copy over here, so the live out becomes a live out prime. So what we had on this side copies over here, and then we just do it again. For you to practice a little bit, I would recommend now that you try to do this on your own. Compute the live in and live out following this procedure, compute it all the way up here, and when you are done, then you check the video. So please pause now, try it on your own now, and then look at my answer. Welcome back. The first one is still the empty set. What is the next one? That we have the live in. Well, it's the use, so it's still the same. So these two things has not changed. But now let's look at the live out from V3. It's the union of the successors in. So the successor of this one is V2, and the in here is x, y, n. So that means we need to have x, y, n there. Okay, so live in of this one is the use, which is x and y, union with the out, x, y, n. So now we should get an n as well, minus the definitions. But we are not defining any n, so we should get x, y, and n here. Next one here, we have x and y, that is the live out. It should be the successors, that is y and x, y, n. So now we should get x, y, n here as well. So it's kind of propagated up. And now the in is the use, x and n, and the out minus the definition, so it will also just stay x, y, n. And then we have the out, which is from the union of the in from the successors. So it's again x, y, n, and then we get the same thing here. All right, so we have computed it, and then the question is, are we done? Well, we have had changes again, so we have to redo and copy it over. But now when we go through here, we will see here that nothing changes. So now we are done and we can terminate. So we can break out of the while loop and we are done with the data flow analysis. Pretty cool. Let's look at some observations. We can see here that we have this variable n here. So this is the parameter. And this is the only thing that is live at the top, which makes sense, right? Because it's the parameter. The variable c here is not live in or live out anywhere, because it's basically only used inside here, and that was kind of hidden here because of this definition. And finally here we see that x, y, n is live out, and that is because of the back loop here. So we have this back loop, and by doing this back loop, that's how we gather this n here when we were iterating. So it's because of this back loop we have to also do the iteration a couple of times. And the purpose of this liveness analysis is to create this interference graph that we will then later use for graph coloring. We should recall now that when we're doing the instruction selection that we talked about in earlier videos, we get a lot of different virtual registers or variables. But we have this limited amount of physical registers, so we need to do something about it. And we know that if two variables are not live at the same time, we can actually use the same physical register. And the purpose is to put as much as possible into the physical registers. So this is why we have this approach with interference, so that if two variables are next to each other in the graph, they are interfering. So the interference graph, we have these nodes, our virtual registers, and the edges specify that we have an interference between the two variables. So this can be caused by either that two variables are live at the same time, or we have some special handling of variables. So when you're using function calls and so on, that you also need to make sure that variables are not interfering. We'll talk more about that in the end of this video. How do you construct this? It's pretty simple. So you go through for each variable. So now we're talking about the variable like x and z and so on. And we create the vertex for each of them. So in this case we have 4 vertices. Then for each vertex v, we do the following. We look at the definitions for each v, and we say that they are called A, And then for each B, which is the live out from that node, we create an edge between A and B. So that means that we'll create an edge from Z to X, from Z to Y, from Z to N, and then from X to X, X to Y, and so forth. And then we do that for this node, and then we keep on doing that for every node. And in this case, we get it fully connected. So they actually connect, all variables are connected to everyone. So basically you got full interference, and it will not be very good when you're doing register allocation. And the problem is already here in the first block. You see that just by using this block, we get this interference graph looking like this. In this particular small example, you will see that it was a little bit conservative here. And you can solve this being less conservative using analysis more at the instruction level. So we can do that. Why do we not always do that? Well, it's because of performance, because this is pretty expensive operations to do liveness analysis. And if we have many more nodes, we get a performance hit, basically. Is there no middle ground? Well, what you can do is to first do it at the basic block level, and then within each basic block you do the analysis again, just for the instructions inside the basic block. And it turns out then since these are straight line code, it's fairly simple to do that. So if we look at, for example, this X, Z, X, Y here, if we do the analysis here, we can just go directly and make these computations. Note here that now the definition Z is just dependent on N and so forth, and this will be an advantage later on when we do construct the graph again. You can do the same thing for this one. In that case, we don't save anything, so we basically get the same set. And if we combine this, so we have these as white boxes here, and then we do this specific instruction level analysis for these two, we have the possibility to construct a new graph. I want you again to pause this video and try to construct the interference graph now with this new method. Do that and then listen to my answer. All right. So the solution is as follows. The main thing you can see here is that there is no dependencies between Y and Z. And the key thing here is that now Z is just dependent on N. Before it was dependent on all the outgoing, like X, Y, and N. The thing is that since we separated that to doing the analysis on each instruction here, we got rid of these dependencies. It's a little bit less constrained. Thank you everyone, and so this video was about how to construct an interference graph and using data flow analysis and liveness analysis. So now we're going to use this to actually do the register allocation, and that's going to be up in the next video. So please continue to watch and subscribe if you haven't done that already. Thank you.